Welcome to the third lecture on properties of triangles. In the last two lectures, we discussed a lot of formulas which were relating the angles to the sides of the triangle. We also discussed three different types of circles which are associated with any triangle. We discussed the circumcircle, the incircle, and lastly also the ascribed circles of a triangle. Starting from this lecture and maybe the next lecture also, we will try to solve some problems which have come in the previous JEE exams and which are related to the topics that we have covered in the last two lectures. So, here is the first problem. So, the problem says that there is a trapezium ABCD such that AB and CD are the two parallel sides of the trapezium, and further that, so there is a typo here, this should be BC. So, AB and CD are parallel and BC is perpendicular to CD. So, it is most probably something like this. So, AB So, we have D here. So, this is the trapezium ABCD, and AB and CD are parallel to each other. Further, it is said that BC is perpendicular to CD. So, what that means is that this angle and also this angle are both 90 degrees. It is said that this length BC is equal to P, and this side CD of the trapezium has a length equal to Q. And the question is asking us to find an expression for the length of this side AB in terms of PQ, and it is also given that so this angle, which is angle ADB, is given to be theta. So, immediately the first thing that we have to find the value of AB, and AB happens to be the side of this triangle ADB. So, now let us denote this angle BDC by phi, and because this triangle BCD is a right angle triangle, from the Pythagoras theorem it is clear that the length of this side BD is going to be square root of P square plus Q square. So, that comes from the Pythagoras theorem, and now we are asked to find the length of this side AB, which let me denote it with R. So, let us now consider the triangle ABD, and because this side AB and CD are parallel, it follows that this angle ABD is also equal to phi, and therefore, this angle DAB is equal to pi minus theta plus phi. And then we invoke the sine law, which we had covered and discussed in the first lecture. So, we invoke and apply the sine law to the triangle ABD, and therefore, what we get is that this R divided by sine theta. So, R divided by sine theta should be equal to this length BD, which is square root of P square plus Q square divided by sine of this angle, sine of pi minus theta plus phi. But sine of pi minus theta plus phi is the same as sine of theta plus phi, and therefore, this equality becomes r over sine theta equals square root of p square plus q square over sine of theta plus phi, from where we finally have r equal to sine theta into square root of p square plus q square over sine of theta plus phi, which can be further simplified. So, in the last slide we had r equal to sine theta into square root of p square plus q square over sine of theta plus phi, and here we will use the sine a plus b formula to expand this. So, we get root p square plus q square into sine theta over sine theta cos phi plus cos theta sine phi, and that is equal to root over, well, now it becomes very simple, because if we go back to the, so if we go back to the figure that we have drawn, and let us consider the right angle triangle BCD, then from here it is easy to find out the values of sine of phi and cos of phi. To be precise, sine phi is equal to p divided by root p square plus q square. Sine phi is equal to p divided by square root of p square plus q square, and cos of phi is q divided by square root of p square plus q square. So, using that we get r to be equal to p square plus q square times sine theta over sine theta into cos phi. Now, cos phi is equal to q divided by, so cos phi is q divided by square root of p square plus q square plus cos theta into sin phi, and sin phi again from this figure is p divided by square root of p square plus q square. And upon simplification we finally see that the length AB is equal to p square plus q square into sin theta divided by p cos theta plus q sin theta. So, this finishes the solution to the first problem. So, let us consider the second problem here, and it says that the angles A, B and C of a triangle are in arithmetic progression. So, what that means is that the angle B is equal to A plus C over 2, and let small or lowercase a, b and c denote the sides, the lengths of the sides opposite to the vertices uppercase a, b and c respectively. So, this in fact is the convention that we have been following so far. So, it is asking us to compute the value of this expression, which is a by c times sin 2c plus c by a times sin 2a. So, a upon c sin 2c plus c upon a sin 2a. So, here we have to use the formula for sin 2c. So, if you recollect, sin 2 theta for any theta is equal to 2 sin theta cos theta. So, using this identity we get this to be equal to 2a upon c sin c into cos c plus 2c upon a into sin a into cos a. Please note that this is an uppercase c and this is a lowercase c, which can be written as 2a. So, we know from the sine law, if you recollect the sine law, then we know that sin c over c is equal to sin a over a. So, this follows from the sine law, and therefore, this and this are the same, and we can actually factor it out. So, that can be factored out. So, then what remains inside is 2a into cos c plus 2c into cos a into, let us say, sin. But we also know that this ratio is also equal to sin b upon small b. So, therefore, here both these factors which are equal are also equal to sin b upon b, and therefore, we write the common factor here as sin b upon b. The angles a, b and c are in arithmetic progression, and therefore, it follows that b is equal to a plus c over 2, which implies that a plus c equals twice of b. But since a, b and c are angles of a triangle, we also know that a plus b plus c is equal to pi radians, and then if we substitute this over here, we get b 3b equal to pi, that is. So, since a plus c is 2b, we have 2b plus b, which is 3b is equal to pi, and therefore, we know that b is equal to pi over 3, and we are going to use that. So, that this is the reason why we have replaced this common factor by sin b over b, because of the fact that they are these angles are in arithmetic progression, we exactly know the value of the angle b. So, this will help us to we do not have to, at least otherwise if we put sin a by a, then we do not know the value of sin a, right, because. And then taking it to the next slide, we have this to be equal to 2a cos c plus 2c cos a into sin b over b, but because b is equal to pi by 3, sin b is square root of 3 over 2 b, and this 2 can also be factored out. So, ultimately what we get is square root of 3 over b into a cos c plus c cos a, and here since we have the cosines remaining, we can use the cosine law. So, from the cosine law we know that the cosine of the angle A is equal to b square plus c square minus a square upon 2 bc, and cosine of angle C is equal to a square plus b square minus c square upon 2 a b. So, these two formulas we had already derived in the previous lectures. So, now we are going to replace the cosine of A and cosine of C by these two expressions, and therefore, what we finally get is square root of 3 over b times. So, A into cos C, which is here. So, essentially the A in the denominator is going to get cancelled, and what will remain is a square plus b square minus c square upon 2 b plus c times cos A. So, the c will get cancelled with this c, and what we have then is b square plus c square minus a square upon 2 b, which is equal to square root of 3 by b into, and after doing the addition here we get 2b square upon 2b, and this obviously is equal to square root of 3. And therefore, in question 2 the value of this expression is square root of 3. So, that also finishes the solution to the second problem. So, this is the third problem. So, in the third problem we have a triangle ABC where the value of the two angles is given. So, essentially we know the value of all the angles. So, let me draw the triangle here. So, A, B and C. So, the angle B is pi over 3, angle C is pi over 4, and it is said that the point D is going to divide the line BC internally in the ratio 1:3. So, we have this point D over here. So, D is chosen such that the ratio is 1:3, and therefore, 3 times BD is equal to CD. And then it is asking us to, so let us also join A and D. So, it is asking us to find the ratio of the sine of the angle BAD to the sine of the angle CAD, which is this angle. And so, it seems that since the sine of angles is involved, it appears that using the sine law is going to be helpful. So, let us use the sine law in triangle BAD, in triangle BAD. So, by using the sine law when applied to the triangle BAD gives us BD over sine of angle BAD. So, BD is the side opposite to the angle BAD, and therefore, this is the ratio in the sine law formula, and this should be equal to AD upon the sine of the angle opposite to AD in this triangle BAD. So, that angle is pi by 3. So, AD upon sine of pi over 3. Similarly, we then take the other triangle which is ACD, and we again use the sine law in the triangle ACD. So, if we use the sine law, what we get is that CD upon sine of the angle opposite to CD. So, the angle opposite to CD is angle CAD. So, CD upon sine of angle CAD equals AD upon, so AD upon the sine of the angle which is opposite to the side AD in the triangle ACD, which is pi by 4. So, AD upon sine of pi by 4. Now, so we basically have two equations now. So, from the first equation we get AD to be equal to sine pi by 3 is equal to square root of 3 over 2. So, therefore, AD is equal to square root of 3 over 2 times BD divided by sine of the angle BAD, and from this equation we get that AD is equal to sine pi by 4 is 1 over square root of 2. So, 1 over square root of 2 into CD over sine of angle CAD, which follows from here. But therefore, However, by just looking at these two equations, it is clear that this expression here and this expression here have to be also equal. They have to be also be equal. So, what we get is that root 3 by 2 into BD over sine of angle BAD equals 1 over square root of 2 into CD over sine of angle CAD, which from which now, since if you remember in the question we were asked to find the value or the ratio, this particular ratio is what we have to compute, and therefore, if we take this term here in the numerator on the right hand side, what we get is that root of 6 over 2 into BD over CD is equal to sine of angle BAD over sine of angle CAD. But we already know that BD from here, we know that BD divided by CD is equal to 1 by 3. So, using this information here, what we get is that sine of angle BAD over sine of angle CAD is equal to square root of 6 divided by 2 times square root of square root of 6 divided by 2 times 3, which is equal to 1 by square root of 6. So, this is the final answer. So, let us now reflect on how we solve this problem. Because the sign of the angles are involved here, we got the hint that we should probably be using the sine law. And then what we also saw was that this side AD is common to both the triangles, and also that the value of the angle opposite to the side AD is also known, and therefore, it is possible to take the ratio of AD to the sine of the angle opposite to it, and that is what has to be computed in the sine law. So, that was what helped us to solve this problem. So, let us look at the fourth problem. It is mentioned that in a triangle ABC, the sides and the angles satisfy this equality, and we are asked to find the value of the angle A in degrees. So, since we have the cosine of A, B and C, and at other places we have the lengths of the sides of the triangles, it immediately comes to mind that we must use the cosine formula. So, that because the cosine formula expresses the cosine of the angle in terms of the lengths of the sides of the triangle. So, if we replace these cosines in terms of the lengths of the sides of the triangle, then the entire equality is in terms of the lengths of the triangle. We know that cosine of A is B square plus C square minus A square over 2BC, and cosine of B is A square plus C square minus B square upon 2AC, and cosine of C is A square plus B square minus C square upon 2AB. So, we will use these expressions here, and what we end up getting is that 2 by A into B square plus C square minus A square by 2BC plus cos B over B, which is this divided by B, gives us plus 2 cos C over C. So, that becomes So, 2 cos C over C will be 2 AB C. We realize that we have A, B, C everywhere in the denominator, and therefore, by just adding all these 3 terms. So, this what we have calculated now is the left hand side of this equality, and since we also see that A, B, C is common to the denominator of all these 3 terms, hence this can be simplified too. So, after simplification what we get is 1 by A, B, C into B square plus C square minus A square plus A square plus C square minus B square plus so this will be, so what we get is 1 by ABC into B square plus C square minus A square plus A square plus C square minus B square over 2 plus A square plus B square minus C square over, so this is as it is. So, we have a divide by 2 here only. So, this A square and this A square gets cancelled, this C square gets cancelled, this here. So, this can then be written as, so only B square remains. So, B square here and B square here. So, what we get is eventually get is A square plus C square plus 3B square over 2ABC. And what was given in the question is, so what we have computed now here is just this left hand side, and it was mentioned in the question that this is equal to A by BC plus B by CA. So, then this by multiplying both the left hand side and the right hand side by ABC, what we eventually get is A square plus C square plus 3B square over 2 equals A square plus B square, and therefore, if we also multiply by 2, what we get is A square plus C square plus 3B square is 2A square plus 2B square, and therefore, what we eventually get is that A square is equal to B square plus C square. And this of course reminds us of the Pythagoras theorem, and otherwise also. So, essentially what we have is a situation where this is, we have a right angle triangle with B and this as C. So, this is C, this is B, and this is A, this is small a. So, it clearly can be seen that the angle A is actually 90 degrees. And otherwise also we know that cosine of A is equal to B square plus C square minus A square upon 2BC, but because B square plus C square is equal to A square, this is equal to 0, from where it obviously follows that A must be pi by 2. And therefore, this also finishes the solution to the fourth problem. So, the answer is that A is 90 degrees. This brings us to the fifth problem. So, it is said that we have a triangle PQR where P is the largest angle and the cosine of the largest angle of the triangle PQR is 1 over 3. Further, the in circle of the triangle touches the sides PQ, QR and RP at the points N, L and M respectively, such that the lengths Pn, Ql and Rm are consecutive even integers. Then it is asked us, so the question is asking us to find out as to what are the possible lengths of the sides of the triangle, the possible lengths of the sides of the triangle. So, for such a question it is most suited to first, so let this be the triangle PQR, and this is the angle P, and it is given that this is the largest angle. So, cos P is 1 over 3 is also given, and this angle P is the largest of the three angles of the triangle. And it is said that the incircle of the triangle touches the sides PQ, QR and RP at N, L and M. So, let us say that the incircle touches the side PQ at this point N, it touches the side QR at this point M and the side RP at this point, sorry, it touches QR at L and it touches PR at M. So, the incircle touches the side PQ at point N, the side QR at the point L, and the incircle touches the side PR at the point M. So, now these lengths Pn, QL and Rm. So, these lengths are consecutive even integers. So, they are all even integers and they are consecutive even integers. So, let us say that this is, let us say it is n, and therefore, this QL has to be n plus 2 and then this Rm is n plus 4. This is because it is said in the question that these three sides are consecutive even integers. And let this be the incircle which I am drawing using the green pen. So, let the incircle be shown in this green color and let the center be here at O. Then, as we discussed earlier in today's as we discussed earlier in the previous lecture, we know that this is 90 degrees and this is also 90 degrees, because the side PQ is a tangent to the incircle at this point N, and similarly here also, and this is the radius R. And if you remember, we had shown that this particular triangle and this particular triangle are both congruent, and since they are congruent, it follows that NQ equals QL, because this is because the triangle NOQ is congruent to the triangle QOL. So, these two triangles are congruent, which implies that NQ is equal to QL, and since QL is n plus 2, we therefore have NQ also to be equal to n plus 2, and similarly this length LR will be n plus 4, and then this length will be equal to this length, which is n. And so, now it was also given, so it is also given that cos of p is 1 by 3. So, let us try to use the cosine formula for cos of p. So, we know that from the cosine formula that cos of p, so cos of p is equal to, so let us say that this length is small q, so q square plus the square of this side. So, we first add the squares of the two sides which are adjacent to this angle P, or basically the lengths of the two arms of this angle P. So, this is q square and this is r square. minus the square of the length of the side opposite to angle P, which is this side. So, let that be P. So, minus P square upon 2 Q R, which is equal to, now this cos P is equal to 1 over 3. So, this is equal to, now Q is equal to 2n plus 4. So, 2n plus 4 whole square plus, and R is equal to 2n plus 2. So, 2n plus 2 whole square minus P square. So, P is 2n plus 6. So, minus 2n plus 6 whole square, and this entire thing divided by 2 times Q times R, and that is 2 times 2n plus 4 times 2n plus 2, and that is actually equal to, so we have a factor of 2 everywhere, as we can see. So, this can be simplified and written as n plus 2 whole square plus n plus 1 whole square minus n plus 3 whole square upon 2 into n plus 2 into n plus 1, which is equal to 1 over 3, and the numerator can be simplified further, and what we have in the numerator is n square. So, there is a 4n over here, there is a 2n. So, we have 6n, but then we have a minus 6n. So, essentially we do not have any term with degree 1 for n here, and the constant will be 4 plus 1 5, 5 minus 9, which is minus 4. So, this is the numerator divided by 2 into n plus 1 into n plus 2. So, taking this forward to the next slide, we get 3 into n square minus 4 is equal to 2 into n plus 1 into n plus 2, which is equal to 2n square plus 6n plus 4, and here we have 3n square minus 12, and then by rearranging all of this we get n square minus 6n minus 16 is equal to 0, and then this can be written as, so this can actually be written as n plus 2 into n minus 8. So, we can factor it out equal to 0. So, from here it follows that n is either 8 or minus 2, but then we if we go back here, we see that this is equal to n, and therefore, n cannot be negative, and hence this solution is not a feasible solution, and therefore, the only possible value of n is 8, which implies that the triangle is essentially, the sides of the triangle are essentially, so 2n plus 2. So, 2n plus 2 is 18. So, this length is 18. So, we have r equal to 18, and we have p equal to 2n plus 6, 2n plus 6. So, that is equal to 22, and the third side q, which is 2n plus 4, is equal to 20. So, that solves problem 5 also, and the possible lengths of the sides are 18, 22 and 20. So, let us take the next problem. If in a triangle ABC B plus C by 11 equals C plus A by 12 equals A plus B by 13, then prove that cos A upon 7 equals cos B upon 19 equals cos C upon 25. Now, since all of these are equal, let us say that they are all equal to t. Therefore, we get that B plus C is 11t, C plus A is 12t, and A plus B is 13t. If we add all these three, so this plus this plus this, on the left hand side we get 2 times A plus B plus C equals $36t. And from this we can see that A plus B plus C is 18t. And therefore, now we can find A, B and C in terms of t. Since B plus C is 11t, by subtracting this from here, we get A is equal to 18t minus 11t, which is 7t. Similarly, by subtracting this from here, we get B equals 60, and then by subtracting this from here, we get C equals 5t. Now, using the cosine law, because we have been asked to find the ratio of the cosine of the 3 angles, and therefore we will use the cosine law, because the cosine law expresses the cosine of the angles of a triangle in terms of the lengths of the sides, and we already have the lengths of the sides known to us. Using the cosine law, cos of A is B square plus C square minus A square upon 2BC, and here I am going to then replace A, B and C by these values. So, let me copy it here. So, then this becomes upon which is equal to 61 minus 49 is 12 t square upon 60 t square, it is 1 over 5. In a similar manner, we just need to now find cos B and cos C also. Cos B is A square plus C square minus B square upon 2AC, which is equal to and this is equal to 74 minus 36 is 38. So, this is 38 by 70, which is 19 by 35. And lastly, cos C is A square plus B square minus C square upon 2AB, which equals which is equal to which is equal to 5 by 7. So, finally, we have cos A is 1 by 5, cos B is 19 by 35, cos C is 5 by 7. And from there, it is easy to see that cos A by 7 is 1 by 35, cos B by 19 from here is also 1 by 35, and cos C by 25 from here it is, we use 5 by 7 here, it is also 1 by 35. So, that finishes the proof. So, here we are asked to show that for any triangle with sides ABC, we are asked to prove this inequality. So, we will try to first prove the upper inequality here, where we are going to use the triangular inequality. So, the triangular inequality states that the length of any side is less than or equal to the sum of the lengths of the remaining sides. So, we have A less than B plus C, and from where we can write that A square, if we multiply both the sides of this inequality by A, we get A square is less than AB plus AC. So, the reason why I multiply with A is because I need to have on the right hand side of this less than equality, I want to have terms which are of this type, and that is why I do this. And then similarly for B, we know that B is less than A plus C, and therefore, B square is less than AB plus BC, and similarly we know that C is less than A plus B, and therefore, C square is less than AC plus BC. And then if we add all of these inequalities, then by adding the left hand sides we get A square plus b square plus c square is less than 2 times AB plus BC plus AC. So, that is what we get after we add the right hand sides of all these three inequalities. And let us add 2 times AB plus BC plus AC to both the left and the right hand side of this inequality. So, what we then get is that A square plus B square plus C square plus 2 into AB plus BC plus CA is less than 4 into AB plus BC plus CA. The reason why we add this is because we would like to show the upper inequality, and the upper inequality has this term which we eventually get. But then we also note that this is nothing but, this left hand side here is nothing but A plus B plus C whole square, and therefore, we have shown the upper inequality that A plus B plus C whole square is less than 4 times AB plus BC plus CA. Next, we prove the lower inequality. So, the lower inequality is not, the lower inequality is also easy to prove. So, we know that A square plus B square minus 2AB, which is actually equal to A minus B whole square, is always non-negative, and from here what we get is that A square plus B square is greater than or equal to 2AB, and similarly we get A square plus C square is greater than or equal to 2AC, and B square plus C square is greater than or equal to 2BC. And then if we add all of these inequalities, what we get is that A square plus B square plus C square times 2 is greater than or equal to 2 times AB plus BC plus CA, which is the same as the inequality that A square plus B square plus C square is greater than or equal to AB plus BC plus CA. And now we add 2 times AB plus BC plus CA to both the sides of this inequality, and therefore, we get A square plus B square plus C square plus 2 times AB plus BC plus CA is greater than or equal to 3 times AB plus BC plus CA. But then this left hand side is again A plus B plus C whole square, and hence we have proved that A plus B plus C whole square is greater than or equal to 3 times AB plus BC plus CA. So, this also finishes the proof of the lower inequality, and we had already proved the upper inequality here. So, this finishes the solution to the last problem of this lecture. So, in the next lecture we will take up some more interesting problems. Thank you.